I've been on mute this whole time. Hello, hello. Can you guys hear me?
You was on mute, Dr.
Yes, you've been mute the whole time.
Yeah, I didn't know. I was sitting here. I gave a whole lecture on probably talked for like at least 5-10 minutes. Okay, so I always start. Good morning, everyone. I'm so sorry. For those that are new to be admitted, I'm going to admit you in from my phone. So that's the only way I'm going to be able to do things. But luckily, we're working with it. My main computer today is not working correctly. It's not allowing me to access the team. So I'm going to be using the main computer for those in class, but also I'll be moving the slides on my iPad covering the same information. All right, so you guys will be able to use the same thing. So for those that need to be admitted in, it might be a little bit slower than usual, but I'll be checking my phone for those students that are waiting in the waiting room currently. Okay. So this point of class marks a very important milestone for us. All right, we're actually moving away from a lot of the looking at molecules and trying to understand how they look in solution, et cetera, to now thinking about reaction chemistry. And typically for most students, this is the meat of organic, right? This is going to be a common theme. We're going to be slowly working through functional groups from now to even second semester, and you're going to learn all the potential, all the major reactions that that functional group can occur, right? So moving among functional groups is very powerful in organic chemistry, but also understanding the reactions are very important as well. So that's kind of what we're trying to slowly work on right now. All right, so this is what chapter 4 is getting us into. Okay, so let's do some basic review of a reaction. Everything on the right-hand side of a reaction arrow is called a what? Yep. If I'm on the right-hand side of my reaction arrow, what is that called? The product. That's right. So I'm hoping everybody's comfortable with that. All right. If I'm on the right-hand side of the reaction arrow, I'm indicating that I'm creating products. All right. That theme is carried over as well in organic chemistry. Okay. That means that everything from the left-hand side had to be in what? A reactant. All right. Keep that in mind. So we know that reactants somehow they're going to be converted into products. All right. That's what we're going to start working on. I'm going to give you a reactant and some reagents, and then you're going to draw a product. Or I might give you a product and tell you to work back to a what? A reactant. All right. So that's the whole basics of what we're trying to do here with organic chemistry. All right. So there's a couple of things that we want to start to think about here: the thermodynamics of a reaction and the kinetics of a reaction. All right, and thermodynamics kind of has something to do with the favorability of products. If you want to think about it, this right here. So there's an energy exchange. It's going to tell you that the change of energy in this reaction is either favorable or unfavorable. And kinetics are just going to explain the rate, right? So thermodynamics has a nice relationship to a word you guys heard in general chemistry, which is equilibrium, right? That tells you to what extent has a reaction occurred. And you guys heard kinetics, right? And rate laws and all that type of stuff to kind of describe how fast a reaction is occurring. And both of those things are very important. All right, they said that you are interested in making a makeup, right? So you might be curious about how favorable is this reaction to make this makeup? How much of the product am I forming at a certain point or at equilibrium state? That would be your equilibrium discussion, right? So you're going to say, well, maybe I get my equilibrium constant is 1.2 times 10 to the third, right? That seems to be somewhat favorable. So that means that your reaction is okay to make your products. But then you might be interested in the rate. Does it take me 2 hours to get to this point? Does it take me 5 hours or 6 hours, right? We know that there's usually a temperature dependency, right? So if I want to speed up a reaction, I can do what to the temperature? Increase it, right? The most important thing in this class, and I know students hate to have to do this, right? I get a lot of complaints all the time, but mechanisms are very important, right? So think about it like this. This is the way I try to first introduce the need to know a mechanism. If I was a mechanic and that told you, hey, my brakes isn't working. And all you can say is that I can only change out what? Your brake pads, but I can't fix why your car isn't braking. That means that there's probably not a higher level of understanding of what? The full mechanism, how the brakes work, right? So that means that you need to hit the brake pedal. There needs to be some pressure that moves into your brake tubes, right? The tubes that move the brake fluid. And then that fluid needs to apply enough pressure to where your brake pads are squeezing on your rotors, right? And when it squeezes on the rotors, that friction allows your wheel to slow down, right? So that whole process is the mechanism, right? How do your car stop when you hit the brakes? All those things in sequence has to happen, all right? The same thing in organic chemistry. I'm asking you, how did compound A get converted into compound B? You're going to have to explain what?
Dr. Cooper, you have waiting to get let in.
The mechanism.
Dr. Cooper.
Yep, I only see one person that's waiting to get in. There's going to be a slow delay on that. I think I mentioned that earlier. I'm using the iPad and the phone. It's a very slow delay. Okay, good. All right, so we need to understand the mechanism. I'm just trying to sell the point. Don't fall lazy, right? It comes off to me as laziness when you don't know the mechanism, right? It just comes off like you didn't take enough time to really learn it. You're just kind of hoping to scoop by. And I understand in life, sometimes I'm not able to give all details, but if you can, this is where you're going to earn your points. And this is where you really have a deep understanding of what's happening. And that understanding will help you in your life, I promise you. Okay, so let's talk about our first process here. We're going to break this down more on Friday. We're actually going to push arrows and really start to break this mechanism down. All right, we want to start working on this chlorination of methane. So our first functional group that we are reacting right now are alkanes. All carbon-carbon single bonds, right? No double bonds, no triple bonds yet. So methane is an alkane. Conveniently, if I take chlorine gas and introduce it to light or heat, and typically we write the letters HB, I'll break that down more on Friday. That's just that's a nice way of saying energy, all right? I will chlorinate methane. I will replace one of the carbon hydrogen bonds with a carbon chlorine bond. And my side product here will be hydrochloric acid, HCl. Okay? So what's very important about this reaction is that I need that light or heat. All right? That's going to initiate this process. All right? And it tells you that if you want to use light to do this, blue color is best. Right? And this is a chain reaction that will occur. All right, so only one photon of light is needed, but this will facilitate a lot of other reactions in pot. All right, so what's key here is to understand what type of mechanism we're going to have to learn to be able to understand this reaction. Okay, I'm trying to work on getting people into class right now. All right, this is a free radical reaction, right? Every free radical reaction has 3 steps. You want to go ahead and start committing these 3 steps to memory. When you show the mechanism, and that's through curved arrows for this reaction, I'm looking for these 3 steps. All right, what are the 3 steps here? There's an initiation step. Initiation has to generate a radical. We'll talk about a radical here shortly. A radical is a single electron carbon species. The second step is propagation. That means that radical converts into a different radical, right? And the last step here is a termination. That radical that I have in solution is terminated to now not have a radical anymore. So typically 2 radical compounds can combine to make a bond, and that ends the radical. All right, so these 3 steps are needed in every free radical mechanism. All right, so if you want to think about, we're gonna talk about it at the end of class today, our reactive carbon species, But I want to go ahead and start talking about the radical because this is the first reactive species that we know. If you had to ask, if I told you that this person was radical, this individual was extremely radical, what would you tell me about that person?
You said if somebody was radical,
Yeah.
they're going against the normal.
Yeah, you can say that. Sure. Person that's radical usually go against the normal. To be a radical person, to go against the normal, you typically have to be very, very unstable, kind of extreme, kind of just like all over the place, right? And that's the same way that we describe a carbon radical. It's extremely reactive, all right? Personally, I'm an organic chemist. I try to avoid radicals at all points. I don't like any radical chemistry. It's just I can't control it. If I generate a radical, I don't know what's gonna do. Right? We try to do a lot of things to control it, but it's too reactive. Right? So keep that in mind. Carbon radicals are extremely reactive. All right? Conceptually or intuitively, why would a carbon radical be so reactive? It's a carbon that has a single electron. All right? So that means that I don't have a full octet of electrons, right? Typically, I need 8 electrons to be happy. If I have a single electron, that means I have 7 electrons instead of 8. So carbon is going to do whatever it can to do what, you think? To gain that electron back, right? I'm hoping that somebody can share an electron with me in a bond. So that becomes extremely radical or extremely reactive. Okay? 3 steps, just break them down, and we'll look at the mechanisms. Again, we'll cover the mechanisms more on Friday. We want to get an introduction today. So the first step here is the propagation step. What happens? Chlorine is going to do a homolytic cleavage. All right? What does homolytic cleavage means? All right? I break a chemical bond where one electron is evenly dispersed on both atoms. All right? Keep this in mind. In the chemical bond, there's how many electrons? 2. So I comfortable with that so far? In every bond, there's 2 electrons, right? When I break this bond, 1 electron in the bond goes to the atom on the right, and the other electron in the bond goes where? To the atom on the left. That's a homolytic cleavage, right? There's only one mechanism type in organic chemistry where we use a homolytic cleavage. And that's when we're generating what, you think? Radicals. Okay? All the other chemistry we'll learn this semester will be a 2-electron process. That means 2 electrons in the bond will go to 1 atom, and they won't split evenly. But right now, we're going to have to split evenly to form radicals. So chlorine is going to break its bond to where 1 electron is on each atom, and we generate 2 chlorine radicals. Any questions with that first step? All right, we'll talk about these arrows a little bit more next semester. Not next semester, I'm sorry. On Friday, next class. But if you guys see here in the classroom, these are half arrow. Right? Can you guys see that? It's not a 2-sided arrowhead, it's a single arrowhead. That's describing the movement of 1 electron. All right, someone has asked to get into class. All right, for you guys that are in teams, yep. Go ahead.
So is that why the halogens have a -1 charge? They're radicals?
No. That's actually when you gain, when you have 8 electrons, they have a -1 charge because of the formal charge.
Oh,
in
okay.
this case here,
So
these radicals don't have a charge.
Okay, that's not okay.
Yeah. That negative charge is just indicating that they're like electrons, right? They have excess electrons. But in this case here, the chlorine radicals, they don't have an excess electrons. They're short 1. I don't know. A chlorine molecule splits homolytically into chlorine atoms, free radicals. And if you guys in teams are looking here, you guys realize this is a half arrow, right? So there's a difference between a 2-headed arrow and a half-headed arrow. The 2-headed arrow is describing the movement of 2 electrons. This is describing the movement of 1 electron. All right, keep that in in mind. Let's put 2 R's here. I'm sorry. Okay. And for you guys that in the classroom, did I bring my markers with me? No, I didn't bring my markers at all. All I'm trying to show is that there's a difference between an arrow that looks like this, right? This describes one electron movement versus an arrow that looks like this. This is a 2 electron movement. All right, is everybody comfortable with that so far? Right, so you want to have this half versus the full 2-headed arrow. All right, keep in mind, basic things like this is what I'm looking for on tests, right? Some students will just draw a double-headed arrow to describe this electron movement. All right, the Lewis structures of free radicals are on this slide here. I'm not going to talk that much about it, but I'm hoping that everybody's under the impression that to be in a radical, I have an odd number. And chlorine has a total of 7 electrons, right? So on the screen here, on the bottle written here, most people just draw the radical with this 1 dot, right? The other 2 pairs or 3 pairs or lone pairs, depending on the atom, are kind of understood, all right, to be there, right? So chlorine radical, this could be chlorine dot, bromine, bromine dot, OH for the hydroxyl radical, etc., right? Okay. The second step in our mechanism is the propagation step. And we said that we can recognize this step because I started with a radical and I ended with a radical. So maybe I should go back here. And I used to teach this differently when I was able to write on the board, but I can't right now. All right. Initiation starts off with no radical and it ends with a radical. So if we need to write that down, I'll write that down. I'll write it on the board in the class. Initiation is typically no radical, I call red, to a radical. Right? That's how I recognize that stuff. But keep in mind, there's a reason why I'm trying to teach this to you guys. I'm probably going to ask you which step of a free radical mechanism is this? Is it the initiation step? Is this the propagation step? Or is this the termination step? Right? So if I started off with no radical in my reactant, but my product has a radical, that's the initiation step. Propagation step is what? I started with a radical and I ended with a radical.
Radical.
Right? That's right. So I'll go from red to red. Right? And for you guys in teams, I'll go ahead and write that. I got a radical that went to a radical. All right. That's how I get, or that's how I identify my propagation step. All right, let's look at this propagation step because it's a very important step here that happens. All right, we call this a hydrogen extraction. All right, again, how many electrons does hydrogen have? All right.
1.
All right, so hydrogen is already a
Radical.
right? So when I say that I'm extracting a hydrogen, I'm just taking the hydrogen atom with its 1 electrons. So let's take a look at the arrows here. It's very important to take a look at this. Chlorine radical has 1 electron. And in the bond between carbon and hydrogen, how many electrons are in that bond?
Wait, can you say that again?
There's 2 there, right? So 1 electron in that bond and the hydrogen atom are going to react with chlorine, right? So they're going to make a new bond here. So if I had to think about this, let's split this up like this. These 2 are going to partner together now to make HCl, and the remaining electron in that bond has to reside back on who? On carbon. That's right. So for you guys in the classroom, I can actually draw on the board here. Let's go ahead and work on this. And that first step is called a hydrogen extraction step. All right, I got my chlorine radical here. its one electron is going to be attracted to one of the electrons in this bond, and the other electron has to remain back on carbon. That's going to give me a new carbon radical plus HCl. Okay? So for you guys in teams, all that I wanted to say there was my new, I cannot erase. All right, this is a pain in the butt today. All right, somebody said they couldn't get in. I'll try my best to call out. All right, give me a few seconds. Somebody said that, I think I saw the last name, Jackson. It's not working on my phone. Here we go. Okay, I'm hoping everybody's getting comfortable here with what they let me. They won't let me erase. All right, but at the end of the day, there's 3 arrows here, right? There's one arrow starting from the chlorine radical, and it's reacting with the second radical arrow right here, right? That's describing the formation of a bond. All right, and that second electron in this bond here has to go back to carbon. So now I get a carbon radical here and my ACO bond. Okay, good. All right. So this next slide is just a publisher's discussion. They want to be thorough, but this won't be a mechanism step for you guys. This is telling you that you can also do another propagation step to actually form the product. All right. So what happens here is that you have your radical or your carbon radical reacting with chlorine. All right. And chlorine doing a homolytic cleavage to now form the product, which is your chloromethane and a chlorine atom, right? However, this is not the step that I want you guys to learn to form your product. Let's move into a different slide here. All right. So it's trying to teach here is that you can do these 2 propagation steps to potentially get your product, all right? This is the termination step that we want to learn from this class, all right? So propagation 2 is just being thorough. You don't need to learn that, all right? We'll talk about how do I get this second chlorine. But if I have that same carbon radical that I formed from my first propagation step, and it's also going to be ACl, right? Okay. Now my second chlorine can react with the carbon radical. Those 2 things will combine to form what? My bond, which is the final product that I want. Right?
So ain't that when these radicals are bond?
It's radical to no rad. That's right. Termination step is radical to no rad. All right. So these are the 3 steps that you want to learn. The first step is that initiation step where I do a homolytic cleavage of chlorine to generate a chlorine radical. That has to happen first, right? So typically chlorine that you have, if you leave it out in the sun, you will form radicals there, all right? So that's why that bottle is typically amber or it's black bottle, right? We'll learn this shortly about hydrogen peroxide also forms peroxide. That's how it works. If you bought a bottle of hydrogen peroxide, what type of bottle is it stored in? A dark bottle. There's a reason why. All right. If you had it in light, it will form the radicals, right? And it will be no good to you, right? It'll just be plain water after a while, right? So that's why they keep it dark, to keep those bonds in order so they can do the chemistry. We're actually going to talk about that chemistry a little bit later in this course. The second step is propagation. I'm going to do my hydrogen extraction. My chlorine radical is going to pull an H off of methane to form a new carbon radical at ACl. And my last step is that from my carbon radical, I can condense, or I'm actually going to be terminated with another chlorine radical. All right, and now it gives me my final product. So it looks like I need 2 chlorine radicals. Did I generate 2 chlorine radicals to do this? So somebody said no. Let's go back. If you look at your first slide here, how many chlorine radicals did you form? 2, right? So that's why we don't have to do that second propagation step. You actually have 2 chlorine radicals to start off with, right? When you did the homolytic cleavage, you generated 2 chlorine radicals, right? The first chlorine radical is going to be converted to which product? ACl, right? So the first chlorine makes ACl, but also a carbon radical. And your second chlorine makes what? So it makes ACl here.
The chlorine.
Yeah, your chloromethane. All right, and your second one is formed to make a product. Okay? We'll try to work those steps out again in detail on Friday. We're going to do some individual products, individual questions, and we'll be working on those. Okay, let's move forward a little bit here. I'm not going to talk about this, the more termination steps. That's not important right now, and I'm going to have to skip over free energy and kinetics for now. Not necessarily ready for that. But I do want to talk about. Go ahead.
So, in the propagation steps, so if we were to initiate a bromine, would we do the same thing that we did to the chlorine, like using the methane and stuff?
Yep, that's right. Okay. Bromine is stored as a diatomic molecule, right? So bromine is typically Br2. Mm-hmm. So that bond also will homolytically cleavage. If you want to think about bonds that typically cleave homolytically, it's bonds that have the same atoms on both sides, right? The bond is polar.
So all diatomic molecules.
Yeah, polar bonds would break heterolytically in one direction, and non-polar bonds would break evenly in both directions. That's right.
Okay.
The steps would be exactly the same for bromine. Okay, so let's just keep working on. And I see that the students are coming in, and it's slow on my end. Very, very slow. I'm hoping that they can get in. All right, I'm going to add you guys again. Okay, so we want to start to talk about the differences between primary, secondary, and tertiary hydrogens. And this is going to have a major influence on which hydrogen is going to be extracted in your propagation step, right? Which is step 2 of our free radical chain. So first, can we recognize the difference between these? All right, primary is coming from how many carbons you think attached? 1 carbon. Secondary means that I have a carbon that has 2 carbons attached, and tertiary means I have a carbon that has how many carbons attached? 3, right? So it's tricky because you need to make sure you're recognizing the carbon and you don't count that carbon. So typically what I like to try to teach is to see that carbon first and then ask yourself how many carbons are attached to that carbon, right? So for those in the classroom, I first identify my carbon, which is here, right? And then I ask myself how many carbons are attached to that carbon. Do not count that one. Sometimes students have this tendency to count. But you can make your life easier if you count the number of hydrogens on a carbon. That always tells you what type of substitution pattern you have. So don't count the carbon that's in the middle because you're trying to figure out what its substitution is, right? So if I ask you what is your height, you don't want to add my height and your height together, right? So it's like you want to talk about that carbon. What is that carbon substitution? But you can count the number of hydrogen on the carbon, and that will tell you indirect pattern. Okay? So if I have 3 hydrogens on my carbon, I have to always be primary. All right? If I have 2 hydrogens on my carbon, I'm going to have to be secondary. And if I have 1 hydrogen on my carbon, I'll be tertiary. If I have no carbons, I'm sorry, not carbons, but if I have no hydrogens on my carbon, I'm going to be what? We call quaternary quaternary carbon. Sorry, I'm saying all kind of words today. It's going to be the quaternary carbon. All right? We don't talk about the quaternary carbon in this class right now, and there's a reason why. Can anybody tell me why are we not considering that carbon right now? And there's a very important reason for this mechanism. To do the propagation step, we call it a what step? Can anybody remember what I call that? I'm extracting a what?
A
Hydrogen,
radical.
right?
Oh,
The propagation step is a hydrogen extraction step. Keep that in mind. Carbon has no hydrogens. Can I do a free radical substitution at that carbon? No. All right, that's the first take-home point. If I don't have hydrogens, I cannot chlorinate, brominate, iodinate. All right, it's not possible for me to do any of this chemistry that I'm discussing. All right, so this is why we wanted to talk about the ones that do the tertiary, the secondary, and the primary. All right, what you guys are going to learn here is the tertiary radical is the most stable radical. Right, so we're going to break down stability of radicals shortly. Tertiary is the most stable. Secondary is the second stable. And primaries are really not stable at all. If possible, they won't form. So the way things work in organic chemistry, the more stable your intermediate, the more favorable the product. If you want to write that down, I'll say it again. The more stable your intermediate, that's going to lead to the major product or the stable product. The most stable intermediate will always lead to the major product. Right? That becomes a very important discussion now in organic chemistry. I'm going to ask you for the major, or I might ask you for what? The minor products, right? Which are side reactants, right? So if you can keep track of the major first, you're doing good. And typically, I always ask for major products. But if I want to be tricky, I might ask you some information about the minor product, right? But right now, we should recognize the major. So let's look at these two reactions. I got 6 primary hydrogens on this substrate. They're all in blue, right? And if I look at the reactivity there, I get the 6% reactivity per H. And if I look at my secondary hydrogens, I only got 2 of those, right? And they're labeled, or they're colored in this pink color. And if I look at the reactivity there, I get what? About 30%. So they broke the math down where they divided those two numbers into each other, and they gave us this nice statement. The secondary hydrogens are about 4.5 times as reactive as the primary. Can anybody tell me why? Why is this the case?
There's less hydrogen. Well,
Not less hydrogens. It goes back to what I just said earlier about stability, right? Mm-hmm. Who's more stable? Is it the primary one or the secondary one? The secondary, right? Because the secondary radicals are so much more stable than the primary ones, that reactivity. All right. And we're going to break that down. Why? Why would a higher substituted carbon be more reactive? All right. And keep that in mind. I'll be using that word, and I'm already using it to describe what it means yet. Substitution, this tells me what's my degree of what's the best way to say it? Carbon attachment. All right. So when I'm saying the word substitution, I'm really asking you, is it tertiary, secondary, or primary, right? How is that carbon substituted? Do I have 3 carbons, 4 carbons, 2 carbons, or 1 carbon, right? The degree of substitution tells me something about its carbon count. All right? Let me see if there's a good slide that describes that here. Yeah, there's one on 38. All right, give me 1 sec in Teams. I'm coming up right now. What's line number is this? 36. Okay. So this is the stability of free radicals. The tertiary radical is extremely more stable than the primary radical. Let's break this down, all right? Let's try to think about this, okay? So let's think about the carbon radical, first of all, as a chemical species. Am I electron deficient or am I electron rich or am I neutral? What will you classify a radical? Neutral, electron rich, electron poor, or electron deficient? Yeah, that's completely right. I'm electron deficient, right? That means I do not have a full octet of electrons, right? So how would I stabilize something that does not have electrons? What will you typically need to do to stabilize it? Give it electrons, right?
Yeah.
If you can share electrons with me, I'll be better off, okay? So this is how it works in organic chemistry. Carbons that have electrons don't mind sharing it with what? Other carbons. Is everybody comfortable with that so far?
Mm-hmm.
So carbons don't mind sharing electrons with carbons, all right? So the more groups that share electrons with me, the more what I'm going to be if I'm a radical. The more stable I will be, right? So out of all these possibilities, which carbon has more sharing groups to stabilize myself? The tertiary. That's right, the tertiary, right? The tertiary carbon has 3 sharers, right? So I'm going to be more stable than the methyl radical, right? That has no carbons sharing to me, right? There's 3 H's. And you guys do know the hydrogen atom can barely share anything, right? Because it has how many electrons total? 1. So it's not even sharing electrons, really. It's holding on to their life, to the one it has, to make a bond, right? So this is how tertiary carbons are more stable than methyl or primary carbons, okay? So the more substituted, and that word pops up all the time, this is no other way to say that but to say substituted. And that means how many carbons attached, all right? The more substituted you are, the more stable you're gonna be. All right, and this explains that reactivity that we just saw. All right, so let's move along here. All right, what slide was this? I want to talk about this 50, slide 50. Give me 1 second here. All right, just to convince those in the room that might be a little questionable with this, all right, there's 2 ways that carbons can stabilize things that don't have carbons. And we're gonna come back to this intermediate. This is a carbon cation, but this is the really good description of this. All right, the term is called hyperconjugation, right? So you know what conjugation means because you guys have learned resonance, right? Resonance and conjugation come together, right? To be able to do localized electrons. Hyperconjugation is a way of doing resonance without having lone pairs and p orbitals all the time. All right, so in this case here, I have an sp3 hybridized orbital that's typically not involved in resonance, but that orbital is able to share electrons, right? And basically what it's saying is that because carbon has these sp3 hybridized electrons and bonds, it doesn't mind doing this hyperconjugation effect to stabilize things that don't have electrons, right? So this is kind of where it comes from. So let's go back one more time. Let's try to break down this last point that I need to make, and then we're gonna end today on our different types of reactive carbons. Slide 33. Okay, 1 sec. I gotta do this 2 more times and we'll be fine. 33. Okay, so we just concluded here that the secondary hydrogens are more reactive than the primary hydrogens, right? So let's see how this looks when I have to consider all possible products, right? So here I have propane, right? And if I look at propane, I have 2 types of hydrogens in this molecule. I'm hoping everybody's getting comfortable with that. I have the methyl hydrogens, and I have that secondary hydrogens in the middle, right? So if I had to look at propane, I would say that this is A and A are the same, and there's B there, right? And for you guys that are in class, I'm looking at propane and I'm recognizing there's only 2 types of hydrogens. There's class A here and there's class B there, all right? Class A will be classified as what type of radical if I drew one there?
Primary.
So draw A. I'm going to remove 1 H for any, right? So this would be a primary radical, A. All right, and for you guys in teams, let's go ahead and draw this out. I'm going to remove 1 hydrogen for any A to make a radical there. And I'm going to generate this right here. And what type of radical will this be for A?
That's the tertiary.
Not tertiary.
You talking about primary then?
Yep, this is primary. That's right. And how do I know this primary? I'm going to put a box. I'm going to underline the carbon I'm interested in, that carbon right there. And I'm going to ask myself, to that carbon, how many carbons are attached?
2.
Not 2, just 1, right? This is right here, right? The methyl at the end is not attached to the carbon all the way there. So I'll ask you guys the same question. I'll underline this in class, right? So how many carbons are attached to that carbon? You would just say 1, just this one right here, right? So this is why that's also known as a primary radical. Okay, good. Now, if I took 1 hydrogen from the B position, let's go ahead and draw that out. Right. What type of radical would that be? Actually, maybe line angle structures would be better for you guys to see this. I can't erase today, can I? Okay, yeah, I can.
Would it be secondary?
Yeah, that's right. Very good. It won't let me do what I want to do here. But this is a primary up top, and this one is secondary radical. Very good. So we look here, our A product is there, or our A radical is there, and our B radical is right there. Okay? And if I look at the course of the reaction, I can potentially get these 2 products, right? I can get a chlorination to form the 1-chloropropane, or I can get a termination to form the 2-chloropropane. If I had to ask you which product would be the major, what would you tell me? Anybody in teams?
Can you reset it?
Yep, the question is, if I had to ask you, from the product that came from terminating at the primary site, which gives you 1 chloropropane, or the product that came from terminating at the secondary site to give you 2 chloropropane, which one would be the major product?
The secondary?
Is everybody comfortable with that so far? No? Okay. You got a question, Mrs. Smith?
I understood that one, but I didn't get it.
do that. A gives me that radical. B gives me that radical, right? If I terminate with a chlorine radical, I'll form this, or form that, right? This is 1-chloro propane. This is 2-chloro propane. And if I ask you which product had to be the major product, you would tell me which one is major. The 2-chloro, right? And how do I know that would be the major product? Because it came from a more stable radical, which was the secondary radical versus the primary radical. All right, so that means that when chlorine has a choice of extracting an H, it's going to prefer to extract an H from a secondary site than it would from the primary site, right? Because that reactivity is different. And the reactivity is different because the secondary radical is extremely stable. Okay. All right, let's end with our reactive intermediates for the day. All right, we'll be talking about 3 of these in this semester. Slide 47. All right, give me 1 sec here in the Teams. Okay. Oh, I don't see you. Can you call in? It won't let you call. But all these slides are already in Canvas. But I'm calling you right now. All right, let's look at reactive intermediates to see if we can make sense of these. All right. Whenever a carbon has a formal plus, all right, there's typically no lone pairs on that carbon. The intermediate is known as a carbon cation. And if I had to ask you for a carbon cation, if that reactive intermediate is it neutral, electron rich, or electron poor, what will you tell me? If I ask you about the carbon cation, if I had to ask you to classify its electronics as being electron rich, electron poor, or neutral, what will you tell me?
Neutral.
Okay. I'll tell you guys. Maybe I should just say it's
a trick question.
Well, it wasn't a trick question, but I'm hearing a lot of stuff that the carbon cation is electron deficient. It's poor. All right. And how do I know that? I don't have a full octet, right? That's how I got that positive charge, right? So again, 4 more charge is valence electron. 6 minus how many lines? 3 lines. Minus, oh, I'm so sorry. Valence electrons for carbon is 4. It's the wrong thing. 4 minus how many lines? 3 minus how many dots? No dots. So 4 minus 3 gives me a positive 1. All right. So I know that that carbon does not have a full octet. And this intermediate is reactive because of that fact, right? So typically you'll learn that carbon becomes reactive when it doesn't have a full what? An octet, that's right. So in this case here, I lost 2 electrons that have a plus charge. The radical, we just learned that one, is a carbon with a single electron. So again, I'm still electron deficient because instead of having a full octet, I only have how many electrons now? 7. I don't have 8, I have 7. And the carbon cation has 6. The carbanion, if I had to ask you if that's electron rich or poor, what would you tell me? What do you think here? This is electron rich, all right? So now I have a carbon with a lone pair in a form of what charge? Negative charge. So this carbon has an octet. Why is it reactive? Because carbon is not extremely electronegative. So it doesn't want to hold on to the lone pairs. It would rather do what, you think? Share in a bond. So that's why a carbanion is reactive, right? Carbanions will burn you. They're kind of basic. You stick your hand in there, they'll try to bond with you, right? You made it a carbon too. You stick your hand in there, it will bond with you. All right. And the last intermediate here is a carbene. All right. Let's count the formal charge for that carbon. Carbon has a valence electron count of 4. How many lines you see? 2, and how many dots you see? So 4 minus 2 is 2 minus 2 dots gives you 0. So carbene has no formal charge, right? It's very unique here. But this compound is reactive because there's an empty p orbital because I don't have a full octet, right? And typically carbenes are bonded to metals, right? There's like a few specific reactions, but carbenes are typically not used a lot in sophomore organic chemistry. All right, I'm just gonna move really quickly through the slides here and you guys will be done. All right, a carbon cation is a molecule that has this empty p orbital, or a carbon that has an empty p orbital. The geometry here is trigonoplanar. All right, the hybridizations are sp2 of that carbon. All right, what's important to keep in mind, because a carbon cation is sp2 hybridized and it has a trigonoplanar shape, all right, that shape is going to dominate the chemistry. Planar is the same way as saying what? I can equally come from the top and the bottom, right? So very comfortable with that? So what we're going to learn here is that I get a lot of racemic mixtures out of this product or out of reactions from carbon cations. What does that mean? I'm going to get reactions where I get both enantiomers in what percentage? Equal percentages, right? That's what it means to be racemic, right? I got 50-50 of both enantiomers. Carbon cations are classic for that. Because it's flat, the nucleophile is going to come from the bottom and the top to give me racemic mixtures. All right? No control over that. All right, again, this ability is very similar to the radical. The more substituted you are, the more stable. So tertiary carbon cations are more stable than secondary, primary, than methyls. Okay? We talked about this ability of carbon. Carbon can do hydrocarbon hyperconjugation. All right, and it can help stabilize molecules that are electron deficient. All right. Another way to stabilize things is through resonance, right? So if you guys look here, this allylic system has resonance stabilization, and this is a great way to stabilize carbon cations as well. Okay. Next, we move into the free radical. All right. We realize that in that p orbital now that's present, we're just going to have one electron there. But again, the radical is still sp2 hybridized. All right. But in this case, we don't have equal attack from the top and the bottom. Typically, I'm going to add an electron wherever that single electron is located. And it could be from the top or the bottom. So there's not a lot of control there. Okay. And we talked about the stability of radicals already. Again, the more substituted you are, the more stable the radical is going to be. So tertiary radicals are more stable than methyl radicals. All right. And again, you guys are going to learn that resonance can stabilize these things. We're going to talk about that in chapter 6. So we will start chapter 6 on Friday. Okay? We're going to be able to stabilize radicals, and that means the number of potential products will change if there's double bonds around. Okay? Carbanions are a little different. They're not sp2 hybridized. They're now sp3 hybridized, right? There's going to be a lone pair in one of those sp3 hybridized orbitals. All right, these compounds are typically reactive. All right, this is a publisher error. The order flips. They got carbon cations here. They didn't talk about carbanions. The title says carbanions, but if you look at the carbons, they all have pluses. This is a mistake from the publisher. The order changes. For carbanions, if you are primary, you are more stable than a tertiary. You want to keep that in mind. Well, I'll say this again when we get to reactions of carbanions, but typically carbanions don't show up until second semester. So we don't do a lot with these yet. All right, we'll talk about the basicity of these carbanions as well. That's a next chapter or a next semester topic. All right, carbenes. Let's end with carbenes. Carbenes are very unique. Not only do they have this empty p orbital, but they also have a area of 2 electrons, right? They have this orbital that contains 2 electrons or 2 lone pairs, all right? So this makes this compound have dual characteristics. I can gain electrons into my empty p orbital, but also I have 2 lone pairs that can make bonds. So a carbene has the ability to make bonds and accept bonds. all right? And this is why they're very commonly paired with metals. Metals have that same property, right? I can add electrons into some metal bonds, but also metals contain electrons that can make bonds, all right? And carbenes has some very unique chemistry. Actually, some really cool chemistry. So if you wanted to summarize our reactive species, a carbon cation has that formal plus charge on carbon, and the tertiary is more stable. I can do the same thing with the radical, and the tertiary is more stable, but the carbon has a single electron, no formal charge. All right, carbanions, this one is done correctly here. The methyl or the primary carbanions are more reactive than the tertiary, so it flips here, all right? And these compounds are typically nucleophiles. We're gonna break that term down next chapter. What's a nucleophile? What's an electrophile? What's a base, okay? And obviously you guys should know what an acid is at this point. We did that in chapter 1, or chapter 2, okay? And a carbene doesn't really have substitution patterns. Again, they're typically bonded to metals, but they have the ability to be both nucleophilic and electrophilic. All right, and I'm just defining what nucleophilic means. To be nucleophilic means I'm looking for a nucleus, so that means they're going to be attacking positive regions. And electrophilic means I'm needing electrons, so that means they're going to typically accept electrons. All right, so they're looking to make bonds. All right, so at this point, we should have some clue about a free radical reaction, the 3 steps: initiation, propagation, and termination. We should have some clue about how those mechanisms work, right? The first step is a homolytic cleavage of a halogen. The second step is a hydrogen extraction to form a radical. The last step is a termination step, right? We learned this ability now on radicals. We're learning that tertiary radicals are more stable than primary radicals. And we understand as well that the primary product or the major product will come from the more stable radical. We'll break that down a little bit more next class. Lastly, we ended today with the discussion of all carbon reactive intermediates. Carbon with a plus is called a carbon cation. A carbon with a single electron is called a radical. A carbon with 2 additional lone pairs is called a carbanion. And a carbon that only has 2 bonds, lone pair, is considered a carbene. All right. We'll talk more about how all these reactive intermediates work in organic chemistry throughout the rest of your organic careers. All right. I'll see you guys in the next class. Be safe. I'm going to stop the recording if there's any questions. Oh, did I mention that it's National Chemistry Week this week? Oh man, I'm doing a bad job of that. I'm the faculty member for the ACS organization. It's National Chemistry Week. Webinar today at 11 is the same day in class. So we missed it, but it's all right. We're going to do a rebroadcast, and we're going to also do a game night with the American Chemical Society soon. It's probably going to be Thursday or Friday. I'm working the details out right now after this meeting, and we will send it out to you guys. It will be for extra credit for this class. So it's going to be a virtual platform. It's going to be like a virtual cafe. You guys will just kind of meet in the virtual platform. We're going to have the webinar that went on today at 11. We'll have that playing, and then we'll ask some questions, and there'll be some potential games and prizes for interested students. We want you guys to appreciate National Chemistry Week. This week the theme this year is sticking with chemistry, which is good. You guys want to stick with chemistry, right? All right. And the theme here really focuses on glues and adhesives, right? So we're breaking down how glues and adhesives are important in our lives. And you guys has definitely probably mailed something that needed a stamp, or you put it on a screen protector that had to be sticky, right? Or you had to use tape to tape things down. We want to appreciate that level of chemistry, right? That makes our life very convenient. I even had I broke some pottery at my mom's house one time. I had to glue it back together. I'm so glad that it was there. My sister picks at me all the time like I'm on for the holidays. You remember when you was a kid, you broke this thing and it's still in the house? I was like, yeah, thank God for the glues, right? So we want to just gain appreciation for those type of things. All right. Thank you guys for listening. I'm going to stop presenting and stop the recording now. If there's any questions,